Good morning all. We want to discuss about electromagnetic theory. Okay, to begin with, let's have a look at the contents. So we are going to discuss about electromagnetism, some historical account, mathematical preliminaries, the equations before Maxwell, Ampere circuital law and displacement current, Maxwell's equation, equation of continuity of charge, Poynting theorem, the wave equation, electromagnetic waves in different media, and the application of electromagnetic field theory. Let's start with the historical account. So historically, these Maxwell's equations were given by Maxwell in 1863. These set of equations represent the relationship between the electric and the magnetic field in the presence of electric charges and currents. These equations represent the most elegant and concise way to describe the fundamentals of electricity and magnetism. In fact, this Maxwell's equations combined two different subjects, electricity and magnetism, into one common subject, that is electromagnetism. Maxwell put together in a consistent and unique way the work done by earlier physicists like Gauss, Faraday, Ampere, Biot, Savart, and others. Remarkably, the Maxwell's equations are perfectly consistent with the special theory of relativity. In fact, Einstein was deeply influenced by Maxwell's work. So Maxwell's equations are one of the most wonderful theoretical work done during that era. This is some of the most significant achievements of Maxwell. He could combine these two distinct subjects, electricity and magnetism, and could even connect light and eventually give the idea that light is an electromagnetic wave. And that's why this is one of the great unification in physics. The first one was carried by Newton, followed by Maxwell. Okay, his work was capable of producing a unified model of electromagnetism, which is considered to be one of the greatest advances in physics. Now, before starting with electromagnetic theory, we need to understand some basic mathematical preliminaries. So to begin with, let's understand what do we mean by gradient of a scalar. So the gradient of the scalar points the direction of maximum increase of the given function. If T is a scalar quantity representing the temperature such that T depends on x, y, z, then gradient of T, read as del T, is nothing but I times del by del x plus j times del by del y plus k times del by del z of this temperature T. So what basically we are doing is we are trying to find the slope of the given function. Okay, this is what we are doing. So by taking the gradient of a scalar field, we try to find the slope in the respective direction. Similarly, let's talk about divergence of a vector. Though you have done it in mathematics, we want to revise it once again. So the divergence of a vector v is the measure of the spread of the vector v from the point in question. So mathematically speaking, if v has three components, vx, vy, and vz, then the divergence of v is given as del dot v, which is the dot product of del with the vector v, and the resultant is del vx by del x plus del v by del y plus del vz by del z. So when you look at these figures, what we realize is that for the first case, the divergence is greater than 0 because the vector field is spreading. So what we notice is that the divergence is positive. In the other case, that is the case of a sink, the divergence is negative because the vector field is compressing inwards. And if the field is incompressible, then we say that the divergence of that particular field is equal to 0. So whenever del dot the vector field v is equal to 0, it implies that the vector field is incompressible. which is shown over here. Okay, in this particular case, the vector field is incompressible. In this particular case, the vector field is showing compression, which means that the divergence of the vector field is negative. Over here, the vector field is showing expansion. Therefore, we say that the divergence is greater than 0. That is positive. Another big thing which we are using over here is curl of a given vector. So the curl of a given vector describes the rotation of the three-dimensional vector field. So at every point in the field, the curl at that point is represented by a vector. Okay, when I have to find curl of a vector f, then the curl of the vector f is simply solving this determinant. We get curl of the vector. So if your field is irrotational, in that case, curl of the vector is 0. For example, in this case, what we observe is that here the curl is 0. While in this case, the direction is continuously changing, the field is curling. So the curl of this vector A is non-zero. Okay. Again, we are going to make use of these basic theorems, which one of them is called the Stokes theorem, and this Stokes theorem beautifully converts a surface integral into a line integral and vice versa. So the Stokes theorem simply says that if f is a vector field, then line integral f dot dl is equal to surface integral curl of f ds. And as you can see in this figure over here, when I find the line integral of the field, then what I am doing is I am integrating over this line from this side to this side and finally over here. And when I am taking curl of this vector field, I am simply taking these small sections along the surface and evaluating the curl along each of these surfaces and adding them together. And this sum total eventually adds up to the line integral. Okay, so this particular theorem helps us to convert a line integral into a surface integral. Another important theorem which is continuously used in electromagnetic theory is a divergence theorem. And this divergence theorem simply converts a volume integral into a surface integral or a surface integral into a volume integral. So what this divergence theorem states is that the integral of a divergence over a region is equal to the value of the function at the boundary. So this divergence theorem can be used to calculate the flux through the closed surface that fully encloses the volume like any surfaces on the left. Okay, so whenever I have a vector A, then volume integral divergence of A dv is equal to surface integral A dot ds. This is what is my divergence theorem. So using the divergence theorem, I can calculate the flux associated with the given surface as equal to the volume integral of the divergence of the vector field over a given volume. Okay. Now the importance of the divergence theorem is that very easily I can convert a surface integral into a volume integral or a volume integral into a surface integral. Okay. Now before Maxwell, this is what was already known. So these four laws were already known much before Maxwell's work, but Maxwell realized the importance of these four laws. So the first one is Gauss law in electrostatics. The statement is that the electric flux out of any closed surface is proportional to the total charge enclosed within the surface. That is, a charge will radiate a measurable field around its area of influence. Okay, this is Gauss law in electrostatics. You can write it mathematically as surface integral E dot ds is equal to Q by epsilon naught. Now let's talk about Gauss law in magnetostatics. The Gauss law in magnetostatics simply states that the net magnetic flux out of any closed surface is always zero. That is, magnetic monopoles do not exist. The third one is Faraday's law of electromagnetic induction, and it states that a changing magnetic flux produces an electric field. The fourth one is Ampere's circuital law, and it states that the line integral of the magnetic flux density along any closed loop is equal to mu naught times the net current passing through the loop. These four laws were already available before Maxwell. What Maxwell did was to connect these laws together and form the important Maxwell's equations. So the first Maxwell's equation is nothing but Gauss law in electrostatics written in a unique way, and that unique way is del dot E equals to rho by epsilon naught. This particular equation is known as the first Maxwell's equation, and Maxwell derived this from the Gauss law by converting it from the integral form to the differential form. As discussed, we can find this del dot E is equal to rho by epsilon naught is nothing but the differential form of the Gauss law. Okay, we have done the mathematics related to this. You can clearly have a look at this. This is the second Maxwell's equation, which is nothing but Gauss law for magnetism. And the Gauss law for magnetism simply says that the net magnetic flux along a closed surface is always equal to 0 because the magnetic field lines are always closed. Magnetic monopoles do not exist. So whatever surface area you consider, you will always find the number of field lines leaving the surface is equal to the number of field lines entering the surface. This particular equation is the integral form of the Maxwell's second equation, and this is known as the differential form of the second equation. It simply implies that the magnetic monopoles do not exist. Let's move on to the third Maxwell's equation. The third Maxwell's equation is simply del cross E, or curl of E, is equal to minus del B by del T, which is nothing but the differential form of Faraday's law of electromagnetic induction. So the Faraday's law of electromagnetic induction is represented in the integral form like this, and when we rearrange it, we obtain the differential form of Faraday's law of electromagnetic induction. This Faraday's law of electromagnetic induction is the basis of the electric generator, and it forms the basis of inductors and transformers also. This forms the third Maxwell's equation. Moving on to the fourth Maxwell's equation. Now this fourth Maxwell's equation, to begin with, Maxwell started with the Ampere's circuital law, right? So the Ampere's circuital law was converted into the differential form, which led to this equation del cross B is equal to mu naught J. Now this particular equation led Maxwell to speculate that there is a discrepancy in this equation, and that discrepancy Maxwell tried to remove by making use of the equation of continuity of charge. Using the equation of continuity of charge, Maxwell could incorporate an additional term over here, which is known as the concept of displacement current. So Maxwell modified Ampere's circuital law and used the modified Ampere's circuital law as the fourth Maxwell's equation. So the fourth Maxwell's equation is with the modification. The other three equations, that is the first Maxwell's equation, the second equation, and the third equation, are direct representation of the laws. Okay, we will discuss about the need for the displacement current in our next lecture, that is part 2 of this lecture. Right now, we'll end till this point. Okay, I'll get back to you. Thank you, class.